This is an introduction for AP students to acids and bases in water. You can read the learning objectives from the AP that I have listed here. Let's review what we know about water. Water involves hydrogen atoms tightly bonded to an oxygen atom. And between adjacent water molecules there is hydrogen bonding, whereby the hydrogen that is covalently bonded in one molecule is attracted strongly to the oxygen of the nearby water molecules. Water, therefore, is a good solvent, particularly for polar molecules like alcohols and ionic substances like salts or strong acids and bases. Water can also act as a weak acid or a weak base. For instance, it will react with sodium, potassium, rubidium, lithium, and it will also react with halogens like bases do. Water auto-ionizes or self-ionizing. Pure water has a small concentration of hydrogen ions and hydroxide ions at all times. This is kind of a modern way to look at it. Two liquid water molecules react, run into each other, and form hydronium ions and hydroxide. Think of two water molecules sideswiping each other. One is gaining the proton of the other. Now both are surrounded by other water molecules. That's what this aqueous means. So hydronium ion is really kind of a mental game that people play. We know that the hydrogen ion itself is surrounded by many water molecules. The hydrogen ion concentration, therefore, is equal to the hydroxide concentration, and that is 10 to the negative 7th in pure water. Therefore, the hydrogen ion concentration multiplied by the hydroxide concentration is 10 to the negative 14th at room temperature, and that is always true. This is a way to think of this happening. The sideswiping producing the hydrogen ion surrounded by water and the hydroxide surrounded by water. So, this is the equilibrium constant for the self-ionization of water. We call it Kw. Hydrogen ion concentration times hydroxide is 10 to the negative 14th, again at room temperature. Now, we're going to define a new function, P. The P of x is the negative log to the base 10 of x. That is, it is the exponent on 10, and it is change the sign. So, P of Kw, which is 10 to the negative 14th, is the negative log to the base 10 of Kw, which is, therefore, 14. Negative 14 is plus 14. And the pH then becomes the negative log to the base 10 of the hydrogen ion concentration, and the pOH is the negative log to the base 10 of the hydroxide concentration. If that's true, then the pH plus the pOH is always 14 at room temperature 25 degrees Celsius. Now let's talk about how to use your calculator to find pH. For a strong monoprotic acid, the pH is gotten right from the molarity of the acid because the acid 100% breaks up into hydrogen ions and an anion. So for hydrochloric acid, if the hydrochloric acid concentration is 0.0024 molar, what you do is you punch the negative key down at the bottom right to get the negative sign. You then punch the logarithm key, which is probably at the top left of your keyboard. You punch the concentration in, 0.0024, and then you push equals, and the pH should show 2.62 for this concentration. That's how you get a pH from the calculator when you have the concentration of the strong acid. Note, The 2 digits after the decimal are there because there are 2 significant digits in the data. 0.0024, 2 significant digits, give you 2 digits after the decimal point in the pH. To find pOH for a strong monobasic acid, like sodium hydroxide or potassium hydroxide, the pOH is gotten again from the molarity of the base. So for sodium hydroxide, if you've got a hydroxide concentration of 0.00039 molar, you would punch again the negative key on the bottom right of your keyboard to get you a negative sign. Punch the log key on your calculator. Push the concentration in this case 0.00039. Press the equal sign and you should show a pOH of 3.41. Note again, 2 digits because of 2 digits, 2 significant digits in the molarity. To get the pH from the pOH, you have a pOH of 3.41 because you're working with hydroxide ions. You simply subtract 14 from that number and change the sign, because the pH plus the pOH is 14. So the pH is equal to 14 minus the pOH. In this case, it would be 10.59, 14 minus 3.41. That's the pH. And of course, 10.59 plus 3.41 is 14. So let's take your turn and you do some, turn off the video, and then check your answers. The pH of hydrobromic acid, given this concentration. The pOH of potassium hydroxide, given this concentration. The pH of hydrogen iodide, hydroiodic acid, given this concentration. The pOH of lithium hydroxide, given this concentration. And the pOH of sodium hydroxide, given this concentration. All of these should do after you turn off the video. And here are your answers to check. Okay, this is Dr. Hubert Alyea's very fine diagram I learned from him many years ago. And this is the kind of thing I would encourage you to draw every time you encounter an acid-base problem. It's a map of the pH and the pOH. We'll rewrite the pH of 1 down here, pH of 14 up here. pH of 7 is neutral in the middle. And you show the large hydrogen ion concentration here with the small pHs, but there's still a little bit of hydroxide present. It shows the linear relationship of the pH to the pOH. pH plus pOH is 14. And it positions strong acids all the way to the left with red, and the strong bases all the way to the right with blue. This is a simplified drawing that adds the pOH, going from 0 on the right to 14 on the left. So let's practice pH and concentrations and tell us whether these are acidic or basic. Turn off the video and then solve the problems and check your answers. Here are the acidic pHs. The pH would be less than 7 here. Remember, this is hydroxide concentration, so the pOH is above 7, but the pH is less. There is an acidic pH less than 7, and all the others are basic. Here's a textbook exercise. Calculate the concentration of hydrogen ions in a solution in which the hydroxide is given here, and another solution in which the hydroxide is given here. You can check your answers after you do the work. And here are the answers to the first question. Or you could just peg the pOH as 2, because this is 1.0 times 10 to the negative 2. Then the pH would be 12, and you simply raise 10 to the negative 12th power. And here's the second solution for the hydroxide ion. Given the hydrogen ion, then And remember always that Kw is equal to the hydrogen ion times the hydroxide ion concentration. Finally, what is the concentration of hydrogen ions in these solutions? Again, turn off the video, solve the problems, and check your answers when you turn it back on. There are your answers.